Welcome back, everybody. The second week of Chemistry of Essential Oils. Today we are going to do some smelling. You have your kits. The way we're going to do this is we don't want to smell directly from these bottles. A perfumer does not evaluate odor by smelling from a bottle. So it's kind of breaking a cardinal rule of odor evaluation to do that. It's okay if you're just kind of quickly wanting to check something out or something, but if you really want to evaluate thoroughly and properly an odor, smell it on a strip, a scent strip. If you don't have a scent strip, get a piece of paper or something, because it's going to smell different than when you smell something out of a bottle. The odor of something can be different depending on whether it comes from a bottle with a big opening or a small opening, and you'd be amazed at how your nose can be deceived by smelling out of a bottle. So that's why we always do odor evaluation on a scent strip. What you'll want to do is take your scent strip, dip it into the one that we're looking at, and then write on the label what it is, bend it up, and then you can, after you're done smelling it, you can set it down. And you'll notice as it dries down that the odor changes over time, okay? Because less and less obviously is there. It's going to be more noticeable on the essential oils, because essential oils are complex mixtures of various molecules which have different evaporation rates, right? So the more volatile molecules are going to go away first, leaving behind the less volatile ones, and you'll notice pretty drastic differences on those over time. The pure components, not so much, because it's just all one component that's slowly evaporating. With that said, before we get into the smelling, we want to first, and I'm going to do this every week, I'm going to take questions on anything that we did last week, okay? That way we can get any kind of misconceptions out of the way before we go into the new material. And also there are people that aren't going to be here for a half hour after start, so it gives them an opportunity to not miss anything new. So I think this will be good anyway, because something will come up, So if anybody wants to ask a question now about anything last week, this would be a good time. If not, then we'll go and start on smelling or hydrocarbons. Nothing? No one has any question? You totally understand all this material from last week? Okay. Not that it's that hard so far. Okay, so this week we're going to talk about the first group, what I call group 1 in aroma chemistry or essential oil chemistry, and that is the hydrocarbons. Okay? From their name you can guess that a hydrocarbon consists of only carbon and hydrogen, right? So these are our simplest class. That's why I cover them first. And the hydrocarbons first I'm going to talk about in general chemistry, and then I'm going to relate it to essential oil chemistry. So there's some subclasses of hydrocarbons, but everything we're talking about today falls under the broad class of hydrocarbon. Okay? So we've got hydrocarbons as our kind of our Roman numeral 1, and then as a subclass here I'm going to talk about first the alkanes. And the alkanes are our simplest type of hydrocarbon. They consist of all single carbon-carbon bonds, right? And we talked about it sort of last week. The simplest alkane would be the one that only has one carbon atom, right? So if we have one carbon atom, and we know that all carbons have to have how many bonds? 4. And we know it's a hydrocarbon, what does everything have to be? Hydrogen, right? So it's CH4. Methane. The geometry of all the carbons in the alkane series are what we call tetrahedral. the unstrained alkane, okay, it's assumed, those of you who've had organic chemistry, you know that when things become strained, these geometries change. But in an unstrained, then the carbon atom will have this tetrahedral geometry, which means if you've ever played jacks as a kid, that's really old, but that's the closest thing I can think of in life that you would have been exposed to that would be in sort of the geometry of a carbon in a tetrahedral geometry, okay? Basically, so methane looks like this in 3 dimensions, where the thick line is coming out at you and the dashed line is going behind the board, and these 3 atoms are in the plane of the board. Okay, that is the arrangement, because everything we're going to be looking at when we look at these skeletal structures is in 2 dimensions, but you have to remember all the time that these are 3-dimensional objects, even though we're not showing them in 3 dimensions, so just keep that in the back of your mind. Properties are generally very unreactive compared to some of the other things we're going to be talking about. Non-polar. Now, polarity is a relative term. If those of you who had organic chemistry, you know what I mean, but polarity is relative to the things that you're comparing. For example, if you're comparing all these molecules to water, they're nonpolar. But when you're comparing them to each other, then you have some differences. So, and what do we mean by polarity? Let's just briefly touch on that. Let's take water, for example. In water, we have H2O, 2 hydrogen bound to an oxygen, right? Because oxygen always has 2 bonds, hydrogen always has 1. And if you look at first week's notes, I talked there about electronegativity of the atoms in the periodic table. And you notice that electronegativity, when you're talking about the periodic table, we have our table here. Let me just draw a little representation of it. As we go up and as we go across, electronegativity increases. Okay, so we've got oxygen over here, and let me just, in this area. So, and hydrogen is basically considered kind of neutral in terms of, so we got oxygen, which is an electronegative atom, which means it likes electrons, wants to pull electrons towards itself. So if you're going to draw dipole moments along these bonds, you've got sort of, these are shared electrons in a bond, in a covalent bond, but they're sort of unequally shared because of one atom likes electrons more than the other. So you've got more sort of electron concentration around the oxygen than you do around each hydrogen. So you got a net polarity of the molecule in this direction, right? That's what we mean when we say polarity. So this is important because polarity determines why liquids are immiscible in one another. So why a lot of these organic molecules don't dissolve in water is because they're nonpolar and waters are very polar. So like dissolves like. And you can dissolve some organic molecules in water, but only very polar ones. For example, acetone will dissolve in water pretty well. Methanol, things like that. But when you get to things like just straight hydrocarbons, let's take hexane, for example, which I'm going to draw 1, 2, 3, 4, 5, 6 carbons. This is our skeletal structure. This is acceptable representation of hexane. I'm not showing any hydrogen, because I don't have to. At each point there's a carbon atom, 1, 2, 3, 4, 5, 6. So we know that it's C6 H what? What's the rule? Right. It's CnH 2n plus 2, right? So if it's 6, this is going to be 14. Always. If it's just a straight alkane, straight chain alkane, no cyclic structures or anything like this, if you know the number of carbon atoms, you can calculate really quickly the number of hydrogen atoms. This, because carbon and hydrogen have pretty much the same electronegativity, there's no polarity introduced into this molecule anywhere. So it's a nonpolar molecule. So it's very, very insoluble in water. And if you dumped hexane into water, you would notice that it forms a really nice, clean layer on top of water. Because it's less dense than water, it's going to float on top of water, it won't dissolve in water. Does that mean none of it dissolves in water? No, there's a tiny, 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 tiny amount that will dissolve, but it's almost imperceptible, or it is imperceptible from a human standpoint. So that is what we mean by polarity. That comes into play, that knowledge about polarity, what it is, comes into play a little later when we talk about things like GC and how that works and how these molecules come off on a GC column and so forth. That becomes important. But knowing that most all these molecules are relatively nonpolar is the reason they separate out from water in the first place when we do the steam distillation to make the essential oil. But again, it's relative, because we are going to talk about polar organic molecules and nonpolar organic molecules. The polar ones are the ones, for this class, are the ones that basically contain oxygen. That's going to introduce polarity. And there are varying degrees of that. Okay? The other thing that is important because of polarity is the concept of hydrogen bonding, which, if you haven't had chemistry in a while, you probably know, you remember it, but hydrogen bonding is this aspect of, okay, we got water, and there are other things besides water that can do this. Basically, anything that has an OH group can significantly hydrogen bond. So you get it with alcohols happening as well. But since you have this slight positive, it's not a true positive charge, we just use this small Greek letter delta. And this is not a true negative charge, but we're saying that there's an unequal sharing of electrons. So we're creating sort of a positive end here and a negative end here. Well, when that sees another water molecule, we can have sort of an attraction now between this hydrogen and this oxygen, because this has a slight negative and this is slightly positive. So there's this attractive forces now that we call hydrogen bonding. It's not a true bond, like a true chemical bond like this is, but it's sort of an extra stickiness that the molecule has that you wouldn't, if this didn't exist, molecules this small they'd be gas at room temperature because they wouldn't be able to stick together, right? So that's why water has a relatively high boiling point. These are pretty strong forces for such a small molecule to be a liquid at room temperature. When you consider that the mass of water is 18 molecular weight. By the way, how did I calculate that? We didn't cover that, but you should know that. Atomic weight of oxygen, 16. Hydrogen is 1. Those are ones you commit to memory. Hydrogen is always 1. Oxygen's 16. Carbon's always 12. And we just add those up. 1 is 2, plus 16 is 18. And then we have methane, which we've got 12, and 4 is 16. Methane is 16. So, yeah, it's a little bit less than water, but if you look at the next one, ethane, which is just this, CH3, CH3, ethane, that has a 12 and 3 is 15, 15, that's molecular weight of 30. So significantly more than water, but yet this is a gas at room temperature, a very volatile gas at room temperature, and this is a liquid, even though the weight is much higher. That's because of hydrogen bonding, okay? This is also the reason why you get, these alcohols boiling at much higher temperatures than the corresponding hydrocarbon and so forth, okay? Again, all basic chemistry revisited. But just kind of keep these kind of things in the back of your mind because we will be talking about them more later. So the properties, again, for the hydrocarbons, for the alkanes that is, are generally unreactive, nonpolar, not water soluble, and actually I should say not water miscible if I want to be correct. We know that, right? A lot of people don't make that distinction. If you're talking about two things of the same phase that don't dissolve one another, we use the term miscible versus soluble. Anyway, and they're less dense than water. Relatively low boiling. And that's compared to their oxygenated counterparts. Of similar weight, okay? Some of the general properties when you're talking about alkanes. Alkanes are considered, they're saturated, what we call saturated hydrocarbons, okay? Which simply means they don't have any double bonds. If hydrocarbons are unsaturated, that means they have double bonds. And so most people are familiar with that term if they haven't had any chemistry with saturated versus unsaturated fat. Now that's a big topic today about the unsaturated fats and things like that. So when they talk about these things, they just mean fats that have double bonds if they're unsaturated. And they're also called, so they're unsaturated. I wish I had more problems again with these. Unsaturated, and also called paraffin hydrocarbons. Make sure I get the spelling right. Two F's, yeah. Paraffin hydrocarbons. Okay. The IUPAC naming method, we talked a little bit last week for alkanes. Pretty simple. Just count up the number in the longest chain, and that, I only said you have to know up to 12, which is dodec. And so figure out how many's in the long chain, and then it's going to be that prefix with the ending ANE. That tells you it's an alkane. Simplest is methane, as we said. Other alkanes that you may be familiar with are things like propane, which is in your gas grill, butane, which is in a lighter, and octane, which is in gasoline. Those are pretty common ones, everyday ones that people are familiar with. Okay, now as far as things that are relevant to essential oils, not a whole lot of alkanes in essential oils. But for completeness, we got to cover them. So as far as essential oils, well, in this field, they're not necessarily significant in the essential oils, but hexane is used in this field in the production of a product called an absolute, right? We talked about an essential oil specifically refers to a product that has been steam distilled, right? Or what? There's only two ways of production that will allow a product to be classified as an essential oil. Steam distilled, yeah. Cold pressed, that's right. And that's only in the case of, right, no. See, not very scientific, but that's just the way it is. So again, an essential oil, geez, what is going on here? Has to be steam distilled, EO, steam distilled. Now, steam or hydro distilled. And the difference there is basically in the way that the steam is generated. A true steam distillation, which is the way most things are done, you have a separate boiler that injects steam into your botanical. A hydrodistillation would mean you have a botanical sitting in the water and you just boil that water and you generate the steam in situ and then produce it. It's a slight difference, but it does make a difference in the quality of the product that comes out the other end. So an essential oil is either steam or hydrodistilled, or in the case of citrus, that are cold pressed. So why am I saying this? Because there are other products in this whole field that aren't produced this way, but are still important. So you have to know this, okay? This will definitely be something that you will be counted to know. If it's not produced one of these two ways, it is not an essential oil. There are other products, though, such as absolutes, which are extracted products, okay? And extraction is a different process from steam distillation. And you will hear people say things, and this is one of those fingernails on the chalkboard thing for me, when people say things like, the method of extraction was steam distillation. If anybody ever says that, they're going to get an automatic F. No, I'm just kidding. But do not ever say that, okay? Because distillation is a completely different process than extraction. When we're talking as chemists, now people to people, they're just talking about, when they say extraction, they just mean a way of getting a product out of something, okay? But we're talking about specific chemical processes here. And if you talk about an extraction, you're talking about using a solvent, whereas distillation is a different process. There's no solvent. That's a big difference, because in solvent extracted products, you can have solvent residues, and they're completely different product. You could take the same botanical, solvent extract it, evaporate the solvent, look at the oil that's there, and steam distill that same herb, and they'll be chemically way different, okay? And we'll look at examples of those later. But there's a specific process of production called absolute, making an absolute, which involves first extracting with hexane to form what's called, well, you extract the absolute. The hexane will pull out not only the volatile aromatics, but it'll pull out heavier plant components like waxes and things like that. Then when you evaporate the hexane, you're left with what's called, I'll say hexane plus evaporation. You're left with what's called the concrete. Then you do an ethanol extraction on the concrete, plus evaporation. And after you do that, you get what's called the absolute. And this absolute should have very little ethanol left in it, maybe 1% or less. We're going to be in trouble here. There we go. I'm just going to throw these away. The absolutes are usually very expensive and highly desired products. Things like Rose Absolute, Violet Absolute, Jasmine Absolute, used a lot in perfumery, very important products, but they're not essential oils. And then after also, and during this process, after you extract this concrete with the ethanol, you're left behind and with, you're pulling out, this ethanol basically pulls out all the volatile smaller molecules, leaving the waxes behind. And so you get a floral wax left over from this process, which is also a product that is sold. Rose wax, jasmine wax, mimosa wax, things like that, they're available. And they are used for different things. Some people use them in cosmetics, they use them in candle making, soap making, all kinds of different things. So I hope that it's visible. So again, go from absolute, do a hexane extraction, form the concrete, extract the concrete with ethanol, evaporate the ethanol, you're left with the absolute. Other products that are important that aren't essential oils are products that are called CO2s, or CO2 extracts. They are extracted with CO2. The way they do that is under pressure and reduced temperature to liquefy CO2 and use that CO2 as the solvent. Now, can anybody think of a reason why that might be a good solvent to use? Right. Bring it back up to room temperature and pressure. There's no, like an ethanol extraction, you have to use vacuum to pull that ethanol off, right? Because ethanol is a liquid at room temperature. Carbon dioxide is just a gas. So as soon as you bring it back up to normal conditions, it's flash evaporates. Now you can recollect that and use it again, but it's a very easy way to get solvent-free plant extract. So, and it's actually a very good product too in the end, but it's expensive to produce because you need carbon dioxide, as some of you probably know. You can't just cool it down to get a liquid, right? Because what happens when you cool carbon dioxide down eventually? It goes to solid. It goes straight from liquid to solid unless you have the right conditions of pressure to make it liquid. So very good products, high quality products, but expensive and not essential oils. All right. Again, still under this category, and that's kind of a side, everything that was just a side note because I don't know that we covered it well last time, but now still under this class of hydrocarbons, I wanted to talk about, they're not very, under alkanes, this is still under alkanes, not very prevalent in essential oil chemistry. And we'll talk about why when we get to the next class. But one that I can think of, and really, well, actually two. A simple one that you'll see is okay, that one. Somebody who's a non-chemistry major, tell me what the name of that molecule is. Nonane, right, yeah. 9 carbons, so it's just straight chain alkane, is nonane. This is found in St. John's wort oil, which is a rare oil. It's not produced in really big quantities, but it is something that's available. It's used in aromatherapy, maybe in some flavor applications, small amounts, but it is produced from the St. John's wort, which is Hypericum perforatum, I believe is the Latin name. And that one is not so common. Probably the most common, and I'll try to hit you with the most common one in each case, is a structure that looks like this. The most common alkane in essential oils is this here. And remember, this is a two-dimensional structure for a three-dimensional object. And that thing. That's a horrible drawing, but this is would be IUPAC named 177 trimethyl tricyclo 2,2,1,0 with the superscript 2,6 heptane. Now, do we want to say that every time we refer to that molecule? No, that's kind of a mouthful. So, essential oil chemists and throughout history, this is just known as tricycline. Tricycline. Now, the important thing to notice here is, and this is, for the most part, there's consistency with the names in essential oil chemistry in that you can look at a name ending in these trivial names and at least know what class the molecule belongs to. But occasionally, you get these kind of confusing things. If you looked at this and you didn't know its structure, you would automatically assume it was a what? You would assume it was an alkene because it ends in ene. But it's actually not. And I believe that, this name goes back more than 100 years. And I think they originally thought that this molecule was an alkene because they didn't really know about these strained kind of crazy structures that could exist because, in the mind of an organic chemist back then, carbon is tetrahedral geometry, and they can vary from that a little bit, but, who's going to think that you're going to change to maybe a 3-membered ring here and then another ring joining these two? That's a pretty strained molecule. It's also, for an alkane, it's very reactive. It would react like an alkene would because they have strained bonds that are easily broken, just like an alkene has a double bond that's easily reactive. So this was originally probably thought to be an alkene. That's where this name comes from, and it still sticks today. So it's just something you got to commit to memory. It's an alkane, not an alkene. So that would be the most common one. It's in a lot of different things in a very small percentage. And I think it's in a very small percentage because it's probably pretty reactive and it will react with other things to form, maybe with oxygen or form a double bond somewhere or something. So it goes on to some other product. But we do see it in small amounts in a lot of different oils. Okay. All right, so, and those just came in, you're going to need your little kits here to smell. This is for week 1. Oh, hydrocarbons. Thanks.
Sure.
All right. The next group, oh man, this would be letter B, are the alkenes. Now, I wanted to just say a little bit about how these things are built up in essential oil chemistry, how the plant builds these molecules up. They all pretty much originate from a product called isoprene. Which is basically a butadiene with a methyl group hanging off of it.
Say isoprene or
Isoprene, sorry. That's the trivial name for that. The IUPAC name would be 2-methyl-butadiene. This is considered the building block of terpenes. Just a little side note, and we're going to talk about more when we get to the terpene section. Okay, but this is an alkene, obviously, because it has a double bond, more than one double bond. But an alkene is anything that has at least one double bond, okay? So the definition is, for our purposes, all you need to know, contains at least one double bond. If it has one double bond, it's an alkene, and there are further subclasses of alkenes that we'll talk about here in a second. Geometry of the double bond, of the carbon where the double bond is what we call trigonal planar. So, in other words, let's just pretend like you have a hydrogen here and hydrogen here. This carbon and this hydrogen are all in the same plane. And there's roughly a 120 degree angle here. 120, 120, 120, it's 360. They call it trigonal planar. Alkenes are what we call unsaturated hydrocarbons. Or also known as olefins. Sort of the older terminology. Names always end in E-N-E. Unless, of course, you're in essential oil chemistry, and then you get things like tricycline, which is not an alkene. So, but in traditional or in formal chemistry, an alkene always ends in E-N-E. An alkane always ends in A-N-E. The simplest alkene, obviously, is just this one, 2 carbons. So then you'd have hydrogen, 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 hydrogen. And this would be called, non-chemist major, what would you call that? What's the prefix for 2? Ethene, right, ethene. That's the formal name for that, but more commonly it's called ethylene. Most people have heard of ethylene. Nobody really calls that ethene, even though that's the real formal name for it. And when you're drawing these structures of these various alkenes, you may see them written in all kinds of different configurations for the same thing. But all that really matters is, you know, the location of the double bond in naming this thing. So here we have a 1, 2, 3, 4, 5, 6, 7, an 8 carbon alkene. And we've got the way we would name that. So we know it's going to be a what right off the bat. It's 8 carbons. It's an octene. But now we have to tell where the position of the double bond is. And so we always number the chain such that the double bond is at the lowest possible number. So if we have a choice of calling this carbon 1 or this carbon 1, we're going to call this carbon 1 because that puts the double bond at the 1 position rather than at the 6 position. So this is just 1 octene. And you could have, you know, you could have a 2 octene. You could have a 3 octene. And 1, 2, 3, a 4, 1, 2, 3, 4 octene. Could you have a 5 octene? No. Why not? Because then you just start numbering from this end. 1, 2, then that becomes 3 octene. Don't worry about it if you haven't had organic chemistry. Just know that when you see this numbering in front of a name of an alkene, that number is telling you the position of the double bond. That's all that is. Okay. The other important thing to notice about double bond and alkenes is when you have a carbon-carbon double bond, it's not like a single carbon-carbon bond. Actually, this would be a little shorter than a single bond. I should. Because if you envision these things as sort of like tinker toys or balls on a rod, on a single bond, these carbon atoms have free rotation around a single bond. Okay? When you have a double bond, because of the way this geometry is, the way a double bond works is you have the sigma bond between this hybridized carbon sp2 orbital that is in the plane between the 2 carbons, and then the second bond is between the lobes of these p orbitals. And these, because of and so then you'd have your substituent coming out of the board, one going back, out of the board, one going back. Because of the way this second bond works, it's called a pi bond, you don't get free rotation around that axis anymore. They're locked into place. So whenever you have a double bond, you have to look out for geometrical isomers that you don't have in this situation, because it doesn't matter what I put here or here, they're not locked into that configuration. Whereas here they are, and if you're going to have 2 things hanging off of each of these hydrocarbons. And if you have big group here, and then say hydrogen and hydrogen, and usually I should be a little bit more chemically correct. And generally we'll use a term R in chemistry, in organic chemistry, which means any general alkyl group. Okay, we're not going to specify what that is. It doesn't matter, because what we're concerned about is focusing on this. So this could be R and this could be R prime, which means a different R. Two big carbon groups off these, when they're on the same side of this double bond, this is called cis, a cis relationship. And that would be put in the name. So that'd be cis, whatever the name of the molecule is. And if we have a double bond and the R groups are opposite one another, this is what we call a trans relationship. And whether it's cis or trans, depending on how the molecule is named, you'll either use cis or trans. Another terminology that will be used, depending on the situation, will be a Z or E. So if you see this Z in front of a name, it means it's a cis isomer. If you see an E, it's a trans. We were always taught to remember Z equals Zaimzide. The German comes from Zusammen, yeah. Okay. Now, probably the simplest, or not the simplest, the most common straight alkene that is not a terpene, okay? Because I'm talking about alkenes now that are not terpenes. Terpenes is a subclass of alkene. Most common simple alkene, NEO chemistry, is this product here. And this is called, I'm not going to go through the formal IUPAC name, this is called xanthine. And anyone who's familiar with anything in essential oils might be able to guess where this name comes from, what oil it was found in, why it's called xanthine. We'll take a guess. Sandalwood, very good, yeah. Yeah, it's the first molecule, the first component that usually elutes in sandalwood, because most everything in sandalwood is heavier components. This would be the first thing that comes off. So it is not a terpene. It's not a monoterpene, and the reason is, as we'll see in a minute, it only has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And as we'll see, like I say in a second, to be a terpene or a monoterpene, you have to have 10 carbons. Don't have an example of this in your kit. I don't even know if it's commercially available. So I couldn't even tell you what that smells like. I've never seen it. All right. Oh, properties. Very similar to the alkanes, but much more reactive due to the presence of double bonds. So similar, everything else is similar. They're nonpolar, they're not soluble in water, pretty much like alkenes, or like alkane, but more reactive because you have a double bond. So now that brings us, so we had A, which was alkanes. We had B, which was alkenes. And now a subclass of alkene here is the terpenes. a terpenes are built up of one or more isoprene units. Built up of one or more isoprene units. So under terpenes now, we're going to talk about, first of all, the simplest terpene is what we call a monoterpene. Now, you can look up, I'm not a botanist, but there are pathways which you can show, which they know how the isoprene is produced from the plant. It's a very common molecule in nature, okay? Isoprene is considered one of the building blocks of nature. It's, the plant emits it all the time. These trees emit it all the time. Anybody here had botany? Nobody? Okay. Anyway, this isoprene then, isoprene itself is not actually involved in the synthesis of the monoterpene, but a derivative of isoprene attached to a pyrophosphate, something like that is, and that's lost. The phosphate group's lost, and then you form the other double bond. Basically, but not really a concern for us. But the monoterpene is basically consists of two isoprene units. Kind of confusing. You call it a monoterpene, but yet it's made up of two isoprene units. But that's just the way it is. So if you imagine, let's take a simple the formation of a monoterpene. You could imagine one such process. Even though this might not occur in a plant, this would be an easy way to imagine, if it doesn't occur exactly like this, how it could occur. Okay, I'm going to show here two isoprene units going to form that, which is called limonene. Okay? Now, for you chemists, you can imagine what type of reaction could we employ to get that? This is simple Diels-Alder, yeah. Basically, you're going to flip this here, this is going to flip down, and that's going to come up. And that's what we call a Diels-Alder reaction. That'd be one route to get there. At this point now, let's look at limonene, since it's one of your samples that you have. So when you smell that, what is the first thing that comes to your mind? And don't say lime. Yeah, should be reminiscent of orange, probably would be the most characteristic. It is in lime oil, but lime has some other things that give it a different character. Orange oil has the highest percentage of limonene of any other essential oil. It's like 95% plus limonene. Okay? Now, if you smell this, now just to give you an idea of how much that small percentage can make a difference, pull up your wild orange now and compare that to your limonene. Quite a bit different, isn't it? You can see that this is in there, right? You can see, but this is way more complex, right? The wild orange. It has a color, right? The color is imparted to it from the peel. But you could actually distill this oil, if you wanted to, from the peel, and it would be colorless, and it would still smell different than just limonene. And if you distilled it, you'd probably be 98% limonene. But that little bit of percentage of these oxygenated components that are also in there, some of these aldehydes and alcohols that are in these citrus oils, they make a huge difference.
The majority of the citrus oils come from the peel or the inside?
They all come from the peel. Now, okay, if it's called a citrus oil, you assume they're talking about the oil from the peel. There are oils that you can get from the flower of the citrus tree, which would be like neroli, or from the leaf, which would be a petitgrain oil. Okay? But when you talk about a citrus oil, they're talking about the peel. No seed. No. So, hey, can we all agree that that's a big difference between limonene and the complete orange oil in terms of the smell? If you can't smell, then I understand you don't see the difference. But, I mean, it's way different, way better, right? Don't you think? It's way more dimensional, deeper, complex. This smells like, man, I could eat that. This smells, it's okay, but no, I don't want to really eat it. It smelled good until you smelled this, right?
So the wild orange is about 95% limonene?
I would say it's somewhere between 90 and 95 on that one. Mm-hmm.
The wild orange is 95%?
Somewhere between 90 and 95, yeah. Pardon? I would say that limonene is probably 99.9 or something. Really, it's highly pure. It would come from an orange oil. It's vacuum distilled off of orange oil. They produce a lot of limonene in the industry as a byproduct of producing what we call a folded citrus oil. And a folded citrus oil just means it's had limonene removed to concentrate those more odoriferous, important components that are oxygenated, like the aldehydes and alcohols that are also in orange oil. So the more limonene you pull off, the stronger that oil is and the better flavor it's going to have for the flavor industry. So you can talk about an orange 5-fold or an orange 10-fold. That means 5 volumes of limonene have been evaporated for every volume that you're left with. So it's, okay? All right. Now, limonene is probably, and I want you to be, this is something you should be intimately familiar with, because it is not only the most common monoterpene, not only the most common alkene, not only the most common hydrocarbon in all of essential oil chemistry, but it is the most common molecule, period, in all of essential oil chemistry. If you gathered up all the essential oils in the world and poured them into one vat, limonene would by far outweigh, if you listed each one and its percentage in that mixture, limonene would be by far number one. And it's used to synthetically make a lot of other aroma chemicals. It's used as a building block for a lot of synthetic aroma chemicals. So, very important molecule in essential oil chemistry. Basically, any of these molecules, anything we cover on any of these molecules are fair game, fair test questions. Okay, because these are, in each group, what I'm covering is the most common molecules of that class that are found in essential oils. All right, so we're still in monoterpenes. I want to hit probably the second most common as well, which would be this one. Which is alpha-pinene. It'd be number 2 on your list of most common of all molecules in essential oils. So let's pull that one out and look at its odor. First impressions on that. Like it? Don't like it? What? Well, that's a good evaluation because it is in cypress. It's the most common component of cypress oil. But do you have a cypress sample that you can compare it to? But it's also in, pine saw, those types of cleaning products. It's probably in almost every essential oil to a small, very small percentage, a fraction of a percent. You could probably find it in just about anything. That's how common it is. It kind of has and someone said this to me years ago, and it always sticks in my mind now, but it kind of smells like stinky feet a little bit to me. Well, that's a good evaluation. I'll put that in my next odor evaluation profile. But alpha-pinene is, now smell that compared to cypress. Let's pull that one out. Now this is there's many different types of cypress, so. Well, not if you smell tea tree oil side by side with it. And I don't know if that's one that we have. I don't think we do. But I can bring that in and you can smell it. If you smell them side by side. Yeah. This is almost all terpenes, monoterpenes, mainly and some sesquiterpenes. Tea tree oil has a large percentage of a monoterpene alcohol in it called terpinene 4-OL. So it's a different feel. Not only different smell, but you get a different feeling from it when you smell it.
Are these still monoterpenes?
Pardon?
Are these still all monoterpenes?
We're still in monoterpenes, yeah. Yeah. So limonene number 1, alpha-pinene number 2, in terms of popularity in essential oils. Beta-pinene would be after that. Beta-pinene is not a part of your kit, but I didn't want to make it too difficult because it's similar in odor. I mean, to me, they're vastly different, but most people that are new to this have a hard time distinguishing between those two, and I didn't want to make it that difficult.
What does it look like?
Looks very similar to this. I think it's just a difference in where this methyl group is. It might be like over here. Don't quote me on that. If you research this on the video, and that's not right, but it's very similar in structure. I think it's just a different methyl group, different position of that methyl group. This is how a lot of times we're not concerned with the specific structure. We're more concerned with knowing what the molecule is and what type of molecule it is, what class it falls under. I can tell you, unless you're into synthetic chemistry, like if you're like into synthesis of aroma chemicals and stuff like that, then your specific structure becomes more important. Okay, I would say this would be a good breaking point before we go on, because